Yo, what's up everyone? My name's Dave and you suck at programming, and today we're going to learn about brace expansion in Bash. Alright, you might be asking yourself, what is brace expansion? Well, brace yourselves, because we're going to find out. Alright, let's take a look. Let's see what we have here. Okay, we have 6 simple scripts. We're going to start with the first one. This one's called simple. This one is just dipping your toes into it. So as you can see here, we have a bash script, and then we echo hello, comma, world, and we have that in curly braces. So what's going to happen when we print that? Well, when we print it, we get hello, space, world. The curly braces go away, the comma became a space. How did that work? Well, hello, comma, world got broken by bash into 2 separate arguments to echo, and then echo ran with 2 arguments, hello and world. So echo separated them by a space, and that's why we have 2 different words coming out of here without the curly braces, without the commas. That's what happened. So let's go into 01. Here's the next example. As you can see, we have the same exact thing, but this time it's in quotes. So what's going to happen now? We get exactly what we put in quotes, all right? So brace expansion only works if it's outside of quotes. If you put it in quotes, the braces won't be expanded. They'll just get treated as literal braces, and they'll be printed to the screen like that. So what else do we have? We have files. So as you can see, this is super useful if we have file names. So like myfile.text, JPEG, movie. Say we have something where we have like a file, maybe like a YouTube video where we have a text description, a JPEG for the thumbnail, and the MOV file for the actual movie file. Well, we can run this, and when we print it, we get those 3 different files. We've kind of expanded into 3 different things. Here's an important note. These files don't have to exist. Brace expansion is not globbing. It's not looking on the file system. It's not checking to see if they exist. These are just strings. There's nothing special about them. We think of them as file names, but they are just strings to bash, okay? Really important to note that. So what else do we have? Well, we can put file names in a variable. So you might be asking yourself, well, if we can't quote it, what can we do? Well, here we have a file name called my-file. We can quote the variable expansion. We can even put more stuff in here and add on to the string. We just have to close the quotes before we get to the brace expansion. This is very important. So if we run this, you can see we'll get the same output. So there you go. Brace expansion works how you expect it. We can also, this part's going to get a little complicated, bear with me. We can have the file name here, my-file, and then we can put that thing into an array. So open a parenthesis and close a parenthesis is how you make an array in Bash. Quote, file name dot, and then the brace expansion here, and we have that in an array. Then we can just use normal array syntax to loop over them and echo each one. So if we run this, we get, there you go. Look at that. We looped over the array and all the file names were stored in the array. So the last thing here is getting really complicated. We can group it all together and we can have something like this. So this is exactly what we saw before. We looped over the array. So at the top, we're going to make an array here. And inside the array, we're going to have /etsy/foo_barbaz/123.text. So we have 2 different brace expansions. We're going to print the number of items in the array, and then we're going to print out what's in the array. So bonus points if you already know what's going to happen here. But bam, there you go. 9 items. Foo123, bar123, baz123. And if you're wondering why did we get 9, that's because we had 3 expansions here and 3 expansions here. 3 times 3 is 9. There you go. That's brace expansion in Bash. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to talk about the sequence command on Unix, SEQ, versus curly brace expansion in Bash, okay, and why you should prefer one over the other. So let's take a look. Let's see what we got here. We got 4 scripts, okay? The first one is called 00 cringe. Let's take a look at the cringe script. This is what you guys think is good, okay? For I in command substitution of SEQ 1 to 10, we're going to echo I. We don't quote this. We actually don't want it to be quoted. If we quoted it, it would break. So we're going to leave it unquoted, and we're going to run this. Let's see what happens when we actually run this command. 00 cringe. We get 1 all the way up to 10. Cool. That makes sense. That's kind of what we expected, right? Let's look at the next script. Why is this one called base? Because it's better. All right. This is the one that I wrote. For I in 1.10 using curly brace expansion, you can put a little pattern here. So we can say 1. This will create a range. And when we run that, we get the same output, but we didn't fork an external command. We didn't have to look out to the system for SEQ. We used all bash built-ins to accomplish that. Pretty neato, right? So let's take a look at why this might be useful, because in this situation, we can actually mix a whole bunch of stuff here. Did you know when you have a for loop, you can just put a bunch of stuff here, as long as you separate it by some sort of white space, you're good. So for I in foo, 1 through 4, 8 through 10, bar. So what's this going to output? Well, let's take a look. It outputs exactly what you think it would output. You just shove stuff in the for loop, and then it just iterates it in that order. Pretty useful, pretty neato. And then what's the last thing we have here? Well, we can get a little bit complex with it. Did you know, I want to say this is like a Bash version 4. I don't remember. Don't quote me here. But you can actually supply a step here. So we want 1 through 10, but then we want a step by 3. So what does that mean? Well, let's run it. 3, complex, run it, and we get 1, plus 3 is 4, plus 3 is 7, plus 3 is 10. There you go. There's some curly brace numerical expansions in Bash. Yo, what's up everyone? My name's Dave and you suck at programming, alright? Today we're going to talk about C-style for loops in Bash. What are those? Why would we even need those? Well, this is really cool, so buckle up. In my last video, we talked about curly brace expansion for numerical expansion in Bash, so taking numbers and creating like a range or something. We're going to go over that, but we're going to show some problems you might encounter and how to fix them, all right? So let's take a look. Let's see what we got here. We have 4 scripts. Let's look at the simple one first. So in our simple script, we do for I in 1.4, and then we echo $i. Very simple, right? Let's run it. Let's see what we get. There we go. So that brace expansion of 1.4 expanded into a range of 1 through 4. Pretty nice, pretty simple. But let's look at the uh-oh script. What's going to happen in the uh-oh script? Well, say you want to set your max up here. Max equals 4, and then we want to loop from I to max. Sorry, from 1 to max, and we want to save that as I. Well, what's going to happen when we run this? Does anyone know? Bonus points if you do. Bam! We didn't create a range. We didn't loop it. We actually just went 1.4 and printed it with literal curly braces. That's not what we want. So how do we do it if we have it in a variable like this? Well, it turns out there's a couple ways to do it. Here's your cringe way of doing it. You want to fork out to an external command and you want to use command substitution without quoting it. This will work. This is fine. It's actually pretty portable if you're going to use this in like shell or something, but we're in bash. All right, we can do one better. So let's take a look at this. We have the based solution. You guys ready for this? Max equals 4. Look at this C-style for loop. If you've never seen this in bash before, you probably just think I'm lying to you and this is some like out of season April Fool's Day joke. But guess what? It's not. We can say for I equals 1. Look, we can even put spaces between the equal signs. I less than equal max. We didn't have to put a dollar sign in front of max. I plus plus. As long as we use the double paren notation, then we're using numerical expansion or arithmetic expression if you were going to look it up in the bash man page. So what happens when we run this? Can you believe it? It just works. It just works, okay? I didn't lie to you. This is real syntax. It works for bash. There you go. C-style for loops and bash. You're welcome. Yo, what's up, everyone? My name's Dave, and you suck at programming. All right, today we're going to learn about globbing in the shell, specifically bash, okay? I've touched on this before in previous episodes, but I'm going to go over the basics today so you understand what's going on. So let's take a look at what we have here. We have a folder called files, and we have a file called notes.txt. Notes is for me, but let's look at file. Let's see what's inside there. Okay, we have 6 files. foo.txt, foo.jpg, bar.txt, bar.jpg, baz.txt, baz.jpg. Cool, so we have 3 text files, 3 JPEG files. Really simple. What are we going to do here? Well, the first thing we can do is we can do ls-1. I don't know if you know about this. It separates the files by new lines. This makes it really easy to see what's going on. So let's do files star. Star will match anything. So there you go. There's our 6 files. It literally matched anything. Star.text. This will match anything up to the end of the string that ends in .text. So anything on the left side could be there. So there you go. We have our 3 text files. We could change that, of course, to JPEG. And there you go, we match all the JPEGs. We could change this to MP3, and look at that. We failed, because there were no MP3 files there. Cool, that's what we expect. On top of that, say we only wanted the foo files, we could do foo.star. And this will match anything that starts with foo. We can do, of course, bar.star, baz.star, and there you go, it'll expand just how you expect it to. There are also some other things you can use, which are super convenient. Say we wanted bar, but we also wanted baz. They're only 1 letter away from each other, and the letter's right here. So what if we made it a question mark.txt? That question mark will match any letter. So there we go, bar.txt, baz.txt. We can do a star here, and then we can match anything that starts with ba some letter dot anything. So you can get really kind of complex with this. You could even tie this down. In my example, it's not going to make a difference, but we could say, you know what, I want an R, I want a Z, or I want a J here. There are no J's, but it matched the R and the Z. We could even say, you know what, I just want R and J. Well, again, there is no J, but we do have an R for bar. So you can use the brace notation or the bracket notation. You can use a star, you can use a question mark, and there you go. That's basic globbing in bash. Yo, what's up, everyone? My name's Dave, and you suck at programming. And today, we're going to talk about extended globbing in bash. All right, in my last episode, we talked about the glob basics. If you haven't watched it, go check it out. You'll learn something there. If you want more extended features, these are little bonus features with globbing, stay tuned. All right, we're going to talk about ext glob. Now the first thing to do is check to see if you have it enabled on your shell. So you can run shopt, this is your shell options, and we can put ext glob. And as you can see, I have it enabled, but if I didn't, you could run shopt-s extended glob, and there you go, that will turn it on. So if you previously had it off, now you have it on, and you are good to go. You have extended globbing. So what does that do? Well, let's take a look. Let's see what we have here. So we have a folder called files. We can ls it. We're going to do ls-1 on files. This will separate them by new lines. And you can see that we have 6 files. foo.jpg, foo.txt, bar.jpg, bar.txt, baz.jpg, baz.txt. All right, cool. So what can we do? Well, with basic globbing, we can do star.txt. And we'll match any of the text files, right? You've seen this before. There's nothing extended about that. But what can we do? We can negate this. So we could put this whole thing in parentheses, and then we could put an exclamation mark in front of it. So you have bang, and then your expression, and we will get now the opposite of it. So we will get no text files. So if we had anything else besides text files, it will match this. We're going to filter out text files effectively with this. We also can do some fun stuff here. So in parentheses, we can do a little bit of regex work, okay? So let's say we want to match foo or bar.text. Now we need to put the plus sign here. Used to the plus sign in regex usually comes after the expression. We put it at the beginning of it. There's a plus sign, a question mark, and an asterisk. Just like in regex, we put it at the beginning of this parentheses, and there we go. So we matched foo.text and we matched bar.text. We filtered out bas.text because we basically used regex here. So like I said before, you might be used to a question mark or a star. You could put it here. This would match, what is a question mark? 0, 1, 1 or many, and then 0 or many. So yeah, look up basic regex if you want to know how to do this. So there you go. There's some basic extended globbing in Bash for you. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to talk about parameter transformation in Bash. All right. Shout out to my buddy Mustache for pointing this out to me. I didn't know this existed. So that's super cool. You might be familiar with parameter expansion. I've gone over that a couple times on this channel. This is slightly different. This is a relatively new feature in Bash. It came in 5.1. I don't know. It's a relatively new feature, but it's super cool and super useful. So we're going to jump right into it, all right? Let's see what we got. We got 4 scripts here. The first one's called casing. Let's take a look at it. So what do we have? We have, hey, my name is Dave. Notice that hey is lowercase and Dave is capitalized. That's going to be important. And then we're going to do 3 different transformations here. So we do s, which is the name of the variable, @ capital U, @ lowercase u, @ capital L. All right, so let's run that. And there we go. So we have all caps, hey, my name is Dave. We have a capital hey, just the first letter is capitalized, and the Dave stayed capitalized. And the last one is all lowercase. So all uppercase, all lowercase, and this one is capitalized like a sentence would be capitalized. So again, to reference, you can see that @ capital U is all uppercase, @ lowercase u is only uppercasing like you would with words in a sentence, and @ capital L will lowercase it. That's super cool. That's super useful. We don't need TR. We can just use these little transformations and get what we want. Let's look at the next one. We have debugging. This is super cool. So we have the same sentence, hey, my name is Dave, and then we have @Q and @capital A. So what's going to happen here when we run this? Well, let's run debugging. So here, this is kind of cool. Q puts quotes around it. It safely quotes a string, and @A does the same thing and put quotes around it, but it makes it a variable assignment. So this is how it would look in a declare statement. This is how it would look if we would assign the variable. So Bash did that. Bash safely quoted it. We didn't try and quote it. Bash did it for us, so we can trust it. How cool is that? What else do we have here? We have special. What's so special about this? Ooh, this is T put setAF1, red T put SGR0. So what's happening here? This is the ANSI escape code. This will print the code to make this text show up as red. It will actually be red on my terminal. And so what we do is we put it with a Q for quoting and an E for expansion. So E will actually expand special characters. So let's take a look at what happens when we run this. So as you can see, the quoted one, this safely quoted what we wrote. We could take this and pipe it into echo. Not pipe it in, we could run it with echo. And then this one expanded it. How cool is that? So we could echo and paste this and we'll get that. What if we take this, copy it, and then echo that? Look at that. See? It was quoted safely, but then when we run it, it will actually give us red output. That's super useful. And then what's the last one? Prompt. So I don't know if you know this, but the PS1 variable, all caps, PS1 is used to set your prompt to a custom prompt in Bash. And there are some built-in variables you can use. So the username is like a \U, the version is a \V. You can look these all up in the man page. If you use @P, it will expand them like a prompt. That's really cool because those weren't variables. That's Bash doing that expansion. Bash put my username there and Bash put the Bash version there. How cool is that? There you go. Parameter transformation in Bash. Shout out Mustache. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to talk about some of the pitfalls with using the timeout command. I don't know if you know about the timeout command. I've seen people use it. You run on your terminal, you would say timeout, an amount of time, and then a command you want to actually run. It's a GNU utility. I believe it's part of the core utilities. So you only find it on a system with GNU utilities unless you install it. But I've seen a lot of people use this in scripts, and there are some things you might get wrong. There's some pitfalls to avoid. So yeah, without any further ado, let's jump into it. Let's see what we got here. So we have a basic command is 00, but the first thing you notice is we have my long command. This doesn't have a number in front of it. So we're going to look at this. We're going to use this command a lot in my examples. So let's take a look at my long command. What does it do? It's a Bash script. We echo starting, we sleep for 5 seconds, and then we print done. There's no secrets here. There's no tricks. It literally does what it says it's going to do. We run it, and it says starting command, and then it hangs for 5 seconds, and then it prints done. Cool. Simple. So let's jump into it. Here's the basic version of timeout. So you do timeout, 1 second, my long command. So this will run the command that's in our current directory, and it will only run it for 1 second. So what happens when we run this? It'll say starting command, and then it will exit right away because it killed it because it went over a second. If we look at the return code, we can see that it had a failure, 124. If we man timeout, Was it 124? Yeah, we can see if command times out and preserve status is not specified. So it errored. It was timeout that gave us that error. Cool. That's super useful. Well, what else do we have? Here's something that I have seen done, and I want to show why this is a pitfall. You can make a function in Bash. Let's make a function called myLongFunction, and it's the exact same as the command, but it's just in a function. Starting function, sleep for 5, echo done, and we're going to run that, but with a timeout of 1 second. So what's going to happen when we run this? Well, guess what? It's going to fail. It's going to fail because timeout is an external command. So timeout doesn't know about the functions in your shell. Timeout is going to look for a program called myLongFunction, and it doesn't exist. There is no program named myLongFunction in my path. It's only in my current directory, and in that case, it was only a function. I can't find it. So what can we do? You might think to yourself, oh, come on, Dave. This is easy. I know better than this. Instead of running the command, we can run bash with a -c, and we can say run myLongFunction. Well, you're onto something, but let's see what happens when we run this. Still doesn't work. That's because we forked bash. We forked and exec a new copy of bash that did not know about the function that we made, the myLongFunction. And that's because functions aren't preserved when you fork and exec bash. So what can we do? Well, did you know this? This is really fun. You can export the function. So we can make a function here, exact same as we've been seeing, export -f, the name of the function, and then we can run timeout 1 second bash -c myLongFunction. There are two types of people watching this video right now, and if alarm bells are going off in your head, then congratulations, you survived 2014. In 2014, there was a vulnerability around exporting functions in bash. It's called shell shock. If you lived around it, I'm so sorry. I was working as a system administrator at the time, technical operations, and my God, did I have to know about shell shock, okay? If you didn't, awesome, go look it up. It's fun little history. If you had to live through it, my brothers and sisters, I'm so sorry, because I did too. But all that aside, what can we do here? We can export that function, and then we can run bash -c. We can run this. Nope, that's the wrong script. We can run this, and look at that. It works. It was actually given to the forked and exec version of bash. How does that work, though? So that's why I made this bonus script. Let's take a look. So we're going to make the function. We're going to export it, but instead of running it, we're going to run a command called printenv. Printenv allows you to print an environmental variable by name. So this is the name of the environmental variable. This is what bash does. Bash will take your function, stringify it, and put it in this variable, bash _func _ the name of your function, %%. Really weird name, really gnarly name, but when you run it, this is what you get. So when bash runs and it sees environmental variables like that, it will take them and parse them as a function and make them accessible into your environment. Super interesting functionality of bash. Just something to be aware of, but you can export functions in bash. So if you're ever in the situation where you want to use the timeout command, this is one way to do it. Yo, what's up, everyone? My name's Dave, and you suck at programming. Hey, look at that. It's on a t-shirt. If you want that, you can buy it. It's on my merch store. That's it. Sponsored content over. Okay, let's jump into it. Today, we're going to talk about the find command. You may have used this command on your terminal to find files. If you're on any sort of Unix-like operating system, you're going to have this command. And it's super useful, but there are there's a pitfall with it. There's a couple different pitfalls with it, but I'm going to talk about one in particular and how to catch it and how to better prepare yourself and fight against this sort of thing in the future when your shell might not be working the way you want it to work when it comes to the find command. Enough yapping, let's jump into it. So let's figure out where we are. Right now, we are in my You Suck at Programming repository. This is where I have every single episode and all the files associated with it. Yeah, there's a lot of episodes of the series. That's pretty cool. So let's go ahead and, in this series, I've talked about cringe and based scripts. So let's go ahead and let's find all of the files named cringe. There you go. That's how we can find all the files in our current directory with the exact base name of cringe. So this will match cringe, nothing after it, nothing before it. It needs to be the base name of the file, and it will print the file separated by new lines. Hey, that's pretty simple. I also have files named based. So there you go. There are all the files named based. But of course, there are wildcards with find. So I can say BASE star, and this will match all of the base scripts as well, right? What's happening here? That's super weird. Basement2.txt. That's really confusing. I don't know what that is. So let's go ahead and see. And we can see that there is a file in my current directory named basement2.txt. Okay, it shouldn't be there. Let's go ahead and delete that. Let's rerun that find command. And what happens? We just get one file. This should match more, right? We search for based. It should be matching all of these, but it's not. So what's going on here? Why is this file here? Let's go ahead and remove basement1.txt and let's reassert that this works. Okay, now it works. So what's going on there? Well, I'll explain it to you because there's two different things here. We can talk about what's going on and how to actually fix it and work around it. So to get started, what I want to do is I want to recreate those files. So we had, what was it, basement1 and 2.txt. So now those files are back created. So if we rerun that find command, you can see that we get the same error that we got at the beginning. This is just to illustrate the concept. So let's jump into this. If there is one thing that you will take away from this video, please let it be this because it is super useful. In Bash, there's a printf command, and printf takes specifier. So I can say %s for a string. And now any arguments I get will get substituted into that string. So foo bar baz, it will print foo new line, bar new line, baz new line. This is useful because any command that you were confused about running, you can put here. So find type f or -name base. So if I run this, we can see the exact arguments that the find command was going to be run with. So we can see what the shell has done if it's done any sort of substitutions or expansions or anything. This is useful because let's go ahead and run base star. This was the exact command we were running before. And what do we get? Look at this. This is how the find command is being executed. It's being called find with the argument -name, basement1.txt, and basement2.txt. So this find command won't work. This is not what we wanted. What's happening here? Well, this expansion right here, this star is being expanded by our shell, not by the find command. So if we want it to be expanded by the find command, we need to actually pass it to the find command by putting quotes around it. Once we do this, notice how it's different. See how this star is not being expanded? The literal star character is being sent to the find command if we execute the find command. So let's go ahead and use this, execute the find command, run it, and it works how we want it to. And look, we also find basement1 and basement2.txt. So there's twofold here. The star was being expanded by find when we pass it to find, but if we don't use quotes, it can't be expanded by find. It can't be a wildcard according to find because find doesn't see a star. It only sees what bash has done to it, and bash has expanded it. So the way you can get around this, use single quotes. This will help you avoid accidental globbing on your shell. And if you're ever in a situation where the command's just not quite working the way you want it to, like if I echo this and I'm like, wait, what's happening? What is echo actually getting? Don't forget this. Printf, and then a string specifier with like a new line or whatever other character, and then you can see exactly how the command was ran and exactly what arguments are being given to it. This way, you won't get any sort of weird scenarios. You can actually make sure that things are being passed to the proper program in the way they expect them to be passed in. So yeah, hopefully this helps you stay away from problems. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to talk about named pipes, specifically how to use them in Bash. They can be used in other languages as well, but in my example, I'm going to use Bash. But these are provided by your operating system, so any other language can open them because they just appear as files on your file system. So let's go ahead and jump into it. The first thing we can do is we can make a named pipe. We can use make FIFO, first in, first out, and the name of the pipe. So we can just call it pipe. And then when we ls, we have a bunch of files in here, but we have that pipe file. If your operating system does not have make FIFO, you might have make NOD, and you can give it the name of the file and then the type of device, so P for pipe. Same thing, it'll create a name pipe for you. There we go, we can just use it. So what can we do with this thing? How does it work? Let's jump into it. The first thing we're gonna do, something rare on this channel, I'm gonna go into tmux because I'm gonna need multiple terminals to show what's happening here. So let me split this. Yeah, I think this way will look good. So the first thing we can do, we have our pipe here. We can cat the pipe. And what's happening? Nothing. Nothing's happening. The cat is hanging. So from the perspective of the operating system, we have asked to read this file, and the operating system is just hanging because there's no data in the file yet, which is nice. Our program will block until data is available. How do we make data available? Well, pretty simply, we can write data to that pipe. There we go. Look at that. We echoed high into the pipe and the pipe above it. Got it. And hey, that's all good. We can go backwards too. The same rules apply here. If I echo into the pipe, we hang. We hang until something reads it. This is really cool because now we can synchronize multiple processes. We could have different threads or processes or subshells. We can synchronize data back and forth by reading and writing to this named pipe, which is shared on our file system. Anything can access it, which is pretty cool. Could be a security nightmare, but hey, we're focusing on the cool stuff, not the security of it. So what can we do here? Let's take a look and see what scripts we have. The first thing we have is our basic reader. So let's jump into the script. Really, really simple bash script. We just read in from the pipe and then we print read line and then whatever we read. So same thing as before, we'll run this, and then we'll go down here and we will write into the pipe. And hey, look at that. We got the data, we put the read line in front of it, and then the script exited. So that's kind of interesting, something to be aware of, that once we get data from it, that read call is done. It's considered end of file. Even though the pipe still exists, it will exit right there. So what can we do about that? Well, we have our second script, forever read. Here is a really simple way of reading from it forever. We just took the original logic and we put it in a while true. Nothing wrong with this. This is totally fine. You run this and same deal. We can just keep piping into it. You can put anything you want. You could say like, who am I, and pipe it into there. And there we go. Users. Will this give a lot of information? I shifted my... There we go. Okay, cool. Awesome. So that's how you can read from a pipe forever in a script. You can just wrap it in a loop. What else can we do? All right, so let's jump into the next script. We have our client writer, but before we run that, let's make sure we have the forever read going up here. And we can go down here, and just like before, we can write into it. No big deal, just like we've been doing. We can also run our forever writer script, or our client writer script, sorry. And so what this does is it takes a name as an argument, and then it loops, and it just writes to the pipe with whatever argument we give it. So if I said, like, I don't know, foo here, this will just run every 3 seconds. It will write to the pipe, and you can see, hey, look, we got the read line that verifies our server's reading it. We got client foo, which is the name of the client that we gave it, and then it prints hello. That's awesome. Why is this useful? Because what if we put it in the background? What if we did that in the background? We put that in the background, and then we put that in the background. And can you start to see what's happening here? We can have one server and we can have multiple clients. So we can have clients writing to it and we could have a server reading it. This way we could have multiple things writing events and one thing reading event. And hey, we can actually start to build something cool with this. So that's pretty awesome. So let's go ahead and kill all of these. How do we do this? Like that? That seems good enough, right? Are all the jobs gone? One more job running. There we go. Percent is just the last job that you put in the background. So if I just run through that list, I should be able to go through and kill them all. Cool. So now nothing else should be running. Awesome. That's great. And then let's move on to the last example here. So the last thing I have here is all in one. So this is an example of why it's useful. In fact, I don't even need tmux for this. So let's break out of tmux and let's look in all in one. So what happens here? There's a lot going on here. If you've never seen the syntax, I'll explain it. The first thing we do is this nice little bash trick where we open a file. This is the name of the file, bidirectionally. So open the file for reading and writing, and we save the file descriptor of it, because every file that you open will have some sort of number, it's the file descriptor, into a variable called fd. So now we have this variable called fd, which represents that file that we've opened. So let's go down here. Let's not look at this function yet. We call client foo and put in the background, client bar and put in the background, client baz and put in the background. And then we just have our forever read here. This is the exact same logic as forever read. The only difference is instead of reading from standard in, we manually specify the file descriptor of the pipe that we open. And then if we go up here and look at our client function, it's the same thing as our client writer function. We take the name as $1, and then we infinite loop write it into the file descriptor. So just like what was happening before, we can do all of this all in one script. That's what I mean by all in one. So you can see that I can open up this file in one script, and then I can have different subshells all communicating with each other. So this is a way of having multiple different tasks in Bash, simulating like threads, or actually in this case, it can be multiple processes, all talking to the same main thread. If you were to do like any sort of like GUI programming, you might know this. You can have asynchronous tasks or different threads, but they all need to communicate back to the one thread that's controlling the visuals that you're seeing. So yeah, this is a pretty cool thing. This is what you can do with name pipes. If you want a more robust example of this, I have a video on this where I talk about a TUI I wrote in Bash that creates a nice little terminal user interface that plays music. I use a name pipe under the hood to handle keyboard events and events like when the song is done playing or if the song fails to play. So you can look that up. I'll link the video if you're interested. It's nightfall.ysap.sh. That's my website. You can go there in your browser and you can look it up. And yeah, that's name pipes in Bash. Yo, what's up, everyone? My name's Dave and you suck at programming. And today we're going to talk about the built-in variable to Bash called bash_env. This is how Bash can read an environmental variable, a file full of environmental variables, and make them accessible to your program. So this is really cool. I'll show you what we have here. If you've ever worked like a project in like a any other language really, you would probably have a env or even a .env file. This will have a list of like variables, environmental variables that you might care about. Maybe you have secrets in here or something. I'll show you an example of it. I have an env file in here, and we have foo equals 1 and bar equals 2. So nice and simple. We don't have to worry about it. So what do? Let's take a look at our basic script. This is our basic bash script, and it's very basic. All we do is say, hello, the variable foo is $foo. So let's go ahead and run that. And we get the variable foo is blank. Of course it's blank. We don't have it set. So what can we do about it? Well, we can set it. If you know any tricks, you can do this. We could say foo equals, hi. And there you go. We can set it for the duration of that script. But did you know that bash can read in that env file and make it accessible to your program? This is actually pretty neat. There is a variable called bash underbar env, and we set it equal to the file that has the environmental variables in it. And then when we execute this script, look at that. The variable foo is 1. It will have read the environmental file, and now all those variables will be accessible. Hey, that's pretty awesome, right? And probably doesn't have any security implications. Well, let's talk about it. So let's move on to our next example, run foo. So this is our next bash script. Here, I'll open it up with syntax highlighting. You can see that we say trying to run foo, then we call a function named foo or a program named foo, and then we print ran foo. So what happens here? Well, let's go ahead and run that script. Trying to run foo, and then we get command not found, because I don't have a command in my system named that, and then we say ran foo. Okay, pretty awesome, but what can we do about that? Well, we have different env files. You notice that we have env extra? Well, what does that do? It defines some environmental variables, but then look at this. It just has raw bash in it. That's because this file just gets executed by bash as a bash file. When I say executed, it gets sourced. It's equivalent of sourcing this file before it runs the script you give it, which is pretty cool, but just be careful with it. Because in this example, we've defined a function here, and now we can pass in that function as long as we specify bash env. So env extra was the name of that file. We go ahead and we run it, and we get hello from foo function. How awesome is that? That is pretty cool. But you may have noticed there was another file in here, wasn't there? What is an env scary? Uh-oh, maybe we shouldn't even look at that. Maybe it's too scary. Let's go ahead and just run it without looking at it. That seems like a lot more fun. So let's run that. Let's run o1 run foo, and let's see what happens. I'm hacking you, LOL. Your system is Darwin. Your user is Dave. Trying to run foo. Hello from foo function. Ran foo. So that's fun. So what's happening here? Nothing really crazy is happening here. This is just to illustrate the point. Look at this. Anything you put in here will get executed by bash. So just be mindful of this. In my example, I still ran the foo function. I still defined the foo function. So you can imagine some sort of hacker or some sort of person with bad intent could put all this, write it to a file that you would never see, and then maybe execute something like this where, hey, let's find all the files on the user's computer and then curl that, post that, or put that to my own, website, web server that I'm running and that you would never know about. Contrived example here, but like the point stands. Anything here will get executed and you may or may not know about it. So that is something to be concerned about. So you might be thinking, that's kind of wild. What do I do about this? Is bash env always being read? Should I worry about this? Yeah, don't worry about it in the sense that you should be afraid, but be aware of it. Know that this happens. This can be kind of crazy. But of course, there's a way we can shut it off. So let's go ahead and let's reset up that command. So I think it was env scary. We run that. We get all that hacking stuff, blah, 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 blah. What can we do here? Well, bash has a command line flag. Of course it does. -p. Go ahead and run -p, and then notice that we get the same output we get if we run it without this bash env. -p is a privilege mode. It tells bash not to do a couple different things like this. So one of the things that bash won't do is read the bash env file. You can go find more if you man bash. You should be able to find, I think it's, can I just search privilege maybe? Yeah, so we have like, here we go, -p, turn on privilege mode. The env and bash env files are not processed. Shell functions are not inherited from the environment. And there's a whole list of other things that don't happen when -p is specified. So be aware of this. This is useful to know. Bash env is very powerful when you want it, but it can be scary when you don't. So there you go. That's bash env and bash. Yo, what's up everyone? My name's Dave and you suck at programming. All right. Today we're going to talk about argmax, the maximum number of arguments you can have. This is in Bash, but this is actually a limit enforced by your operating system. So have you ever seen an error message like this? You're running something on the terminal, maybe you're giving it a lot of arguments, or you're having like expand over a glob, maybe you have like a star here, trying to ls star, and there's just too many files, and you get that weird message like argument list too long. Let's talk about it. Let's figure out what's going on. So I'll show you some examples right here. We're on Bash, so of course we can run echo 1.10, and this is curly brace expansion. It will expand that into 1, 2, 3, 4, all the way up to 10. That's cool. I can make sequences here. Well, what's actually happening? The way we can figure this out is we can use printf. So let's printf. We have numbers, so we can use %d as a number specifier, and then we'll put a new line after the number. So for every argument we give printf, we're going to print it like a number, put a new line, and then do that for every single argument. This is something really cool about printf and bash. That's how it functions. So what does that mean? Look what's happening here. Every single number that's generated here is being passed as a separate argument to printf. This is important. We can prove this. I have a little helper script here called args. Args is a really, really simple script. It just tells you the number of arguments something was called with. So if I call args on its own, we get 0 arguments. If I call args with foo, bar, baz, we get 3 arguments. If I call with 1.10, we get 10 arguments. Hey, cool. That's awesome. So what can we do here? What if we give it a lot of arguments, like a lot of arguments, like 3, 1, 2, 3. How about 1,000,000 arguments? Will this work? Yeah, it does work. It's kind of interesting. It seems like 1,000,000 would be too many, right? We can go ahead and pipe this to dev. There's too much data here. Let's just write it to dev null, so this way it can actually kind of go a little bit faster. So did that work? It worked. So why did that work? Well, here's why it worked. Echo is a shell built in. We're not forking and execing an external tool. We are using the shell built-in echo. There is bin echo. There is an external command tool, or a command, external command that we can use. So what does that mean? Let's go ahead and rerun that same echo command, but let's use bin echo instead. There we go. Argument list too long. That's because we were trying to write it to an external command and not to the built-in. So what's happening? What is this limit? Is there a limit to the number of arguments we can have? Kind of. Different operating systems will have different ways of showing this. I'm on my Mac. I think this works on Linux as well. You can do getconf argmax, and you can see we have this number here. What is that number? Well, I won't keep you in suspense. That is 1 times 1024. Ugh, didn't type that right. Times 1024 times 1024. That's what that number is. That is 1 megabyte. So the argmax is 1 megabyte of data. There's a reason for this. It's because the arguments are going to be passed through the stack, and there's like a limited amount of memory space for that. So the limit itself is not number of arguments, it's the size of the argument data. There's some other logistics behind it, and different operating systems will handle it differently. So it's not like 1,000,000 is going to be a magic number here. There's just going to be a certain point where you will hit this limit. So here, I can actually illustrate that. We counted up to 1,000,000, and we use the built-in echo. That will work. We can save this. We can save this into a variable, and now we just have a really large string named $S. So $S, if we were to run it through bin echo, it still fails. But wait, wasn't there only one argument? $S is just one argument. Yeah, so you can see argument list too long. It's only one argument, but it's just too big. So it's not a number of arguments. It's the total size of the argument. So whether you have one argument that's gigantic or 1,000,000 small arguments, you're going to run into the same issue. So what can we do about this? Well, if you use the bash built-ins, you avoid this. You don't have to worry about it. It's actually the process of calling exec, the fork and execing on your system to create new processes. It's the exec syscall that's failing to run here. So built-ins, hey, that's going to work totally fine. You got a function in bash and you want to take 1,000,000 arguments? Yeah, that's fine. Probably be slow, but it'll work. So let's talk about ways to get around this. The classic one, the one that I really like, is xargs. So let's talk about this. We had that printf before, where we did this. Let's do 1 up into, let's just do 100,000. We don't need to go to 1,000,000. Million's a little bit crazy. We can pipe this to xargs bin echo, and hey, it works, right? This looks amazing. That's exactly what we wanted. How did that work? Well, I'll show you. Let's pipe it to our program called args. Look at that. Do you see what happens here? It batched them up. So this args program was called this many times, and each one was called with 5,000 arguments. So xargs is aware of the limits. Xargs is the program that batch them up. If you're using a basic version of Xargs, it should work. If you have the GNU version of Xargs, I think there's even ways to see the limits and all sorts of things like that. There's parallelization options. Xargs is wild. It's probably going to be the topic of its own video. But for now, this is how you get around argument list too long. This is why it happens and how to deal with it with external tools. So yeah, there you go. Yo, what's up, everyone? My name's Dave and you suck at programming. And today, we're going to talk about exit codes on Unix and Unix-like operating systems. We're going to be using Bash, but this applies to any programming language out there, really, because this is more specific to the operating system. But yeah, we're going to talk about exit codes and one very specific pitfall you got to watch out for, something to be aware of that you may not even know. So yeah, let's jump into it. So the first thing we have here is a nice little script called simple. This is a very simple script, right? We echo hello. That's all we do. It's a Bash script. You run it, and it echoes hello. Why is this important? Because what is our exit code here? 0. It worked, right? We exited with 0. That's awesome. We didn't explicitly call exit 0. We didn't have that here. Nope. We just let the script run and it exited successfully. Why did it exit successfully? I'm going to show you a fun little trick about this. Because what if it failed? Can I make this fail? How can I make echo fail? Well, actually, what if I wrote it to dev full? This is a device that exists in your system that's always going to simulate a device that's always full. So if I run this, operation not permitted. We can't write to it. What if I run this now? We get an exit code of 1. Isn't that interesting? Our script, which doesn't explicitly call exit anywhere, failed. How did it fail? That's because when we're in Bash, the exit code, if not specified directly, if we don't call exit here, or even if we call exit without an argument, it will be the command that was last run. So we get the exit code of echo here for free. That's how it works. If you want to override that, we can look at the next one. Let's look at failure over here. We have uh-oh, and then we exit with 1. So the cool thing about this is it will always echo with 1. There's nothing we could do. Even if we were to write it to dev full, I mean, what would this do? It would just cause it to echo 1 anyways. But it's the same thing. We get an error, but we get 1. The reason we get 1 is because we very explicitly state we want to exit with 1. And look at $? That's how you can get that information. It's 0 here because ls was the last command that ran. So what can we do here? I'm going to illustrate a concept for you. Let's look at this script. Let's take the code from the user as the first argument and then exit with that code. Okay, cool. What does this illustrate? Well, if we exit with 50, we can echo $? And we get 50. That's pretty cool. If we exit with, I don't know, 200, we get 200. It's almost like an HTTP status code. It's not. Don't think of it that way, but you could think of it that way. You might be thinking, oh my God, if I wrote a program like curl or something, I could just exit the status code directly, right? That won't be a problem because if I want to simulate a 404, like they try to get a file that doesn't exist, we could just exit 404 and they get 148. So yeah, not that great. What's going on here? How can you get 148 from 404? That seems kind of interesting. Well, 200 seemed to work, right? So let's go ahead and let's try and find where the problem is, right? So 300 gives you 400 or 44. So what's going on here? What's 300 minus 44? Maybe that's a way to work through this. I don't know. Let's try 254. I already know the answer. That's why I'm cheating here. 254 gives us 254. That's great. 255 gives us 255. That's great. 256 gives us 0. And now we've wrapped around. So what's going on here? We can exit in Bash an integer. We have 64-bit integers. They might technically be slightly less. I don't know. Don't quote me on that. We basically have 64-bit integers. The problem is the exit code from the operating system chops off everything. It only cares about the last 8 bits, so it will truncate everything to an 8-bit number. This is effectively the same as modularly dividing it by 256, or 2 raised to the 8th power. So that's how we could calculate this beforehand. So like before, when what do we do? 404, and that gave us 148. We can modularly divide this by 256, and we will get 148. That's how that's determined. Now this is the same in any programming language. If you're in C and you try to return 404 in your main method, it will show up as 148 for the program that's calling it. So that's kind of a problem. Why is it a problem? Because I've seen code like this in the wild. I have seen people write code like this, where they set code equal to 0, they loop over an unbounded number of arguments that a user can pass in, and then they do some work. In this example, we're just trying to SSH in the machine. This is a contrived example. They're SSHing the machine. If it fails, they increment the code. Now, this might seem like a good idea. I know I named the script bad idea. I'm kind of, forecasting that it might not be good. But let's imagine we try to give it, 3 arguments here. We tried to SSH in all 3 of those. We got problems. And now our exit code is 3. So we know 3 machines failed. It seems like this would be useful, right? If I gave it 5 arguments and we had an exit code of 3, we know that 3 out of the 5 failed. That's not great. That seems like it's useful to transmit that information, but why is this a problem? This is a problem because what if I wanted to SSH into the whole entire IP range, into 256 hosts? What happens now? Well, we get a lot of failures. And then when we run we check the exit code, it looks like it exited with 0. It looks like it's successful. It didn't. We exited with 256, but that data was lost. We can't find this. So if you ever find yourself writing code like this, stop. Don't do that. Do this idea instead. This is what you should be doing. Instead of incrementing this code, because you increment it based on the amount of arguments the user passes, you're secretly letting user data influence what you, the programmer, what this program actually does. You might not realize it, but you're letting user data influence how this program acts. That's not good. You can change how the program acts, but you can't change the data the program returns. That's the distinction I'm trying to draw here. So in this example, if any SSH command fails, we just set this to 1. This would be no different. A different way to write this is we could say error equals 0. Otherwise, error equals 1. We're using exit codes here, so that's what I'm talking about. But the example here, the idea here is that we set the error flag to 0. If any one or many SSH commands fail, we just turn on the flag. If a subsequent one fails, it basically has no effect here because the flag was already turned on. This is a better way of doing it, so then when we exit this code, we don't have to worry about it wrapping at 256. We have a very strict binary of, did this work, yes or no. So this is the proper way to handle exit codes. Yo, what's up everyone? My name's Dave and you suck at programming. I got a real quick tip for you. You can syntax check bash scripts really easily using bash -n. And there's a couple cool things you can do with it, but I want to kind of dive into it. Let's take a look at this. We have 2 scripts in here. We have good syntax and bad syntax. Let's look at good syntax. This is a completely normal script. This is a working script, nothing weird here. The beauty of this is, I don't know if you knew this, you can run bash on the script to execute it. You can run bash -n on the script to syntax check it. Notice that it exited successfully and didn't print anything. That means that that bash syntax is good. Now you might be thinking, well, I just use shell check for this. Shell check is an amazing program to syntax check my stuff. And you're right, shell check is amazing. I love shell check. I use it all the time. But shell check does a lot more than just syntax check. It has like lints, it has all sorts of warnings. It can, it's really involved. This is a very simple binary of, is this syntax valid, yes or no? But it's even more than that. Because remember, shell check is an external program. It doesn't know what version of bash you're going to run your script against. Whereas by contrast, I'm executing a very specific bash interpreter here, and I'm asking the bash interpreter, hey, you, this specific bash interpreter, are you able to run the contents of the script? Are you able to understand this, yes or no? This is really good because imagine if I had newer syntax and an old bash interpreter, that old bash interpreter might choke and bash -n will return a failure. Whereas shell check would be like, oh yeah, that's newer syntax, but I'm okay with it. This is a real nice way of asking the interpreter, can you handle this? So of course, I also have a bad script here. This is syntax that doesn't work. So we can see I am here, and then we have this if statement where we're missing this little square bracket there. So if we go ahead and try to run it, we get this, it doesn't work. Notice how we have the line I am here, and then H was given. It doesn't even bother checking that. There's nothing to do. We just have bad syntax. So why is that useful? Well, we ran the script and we got I am here, meaning it executed what was inside it. If we do mash -n, we just get the error messages. We don't get I am here. Nothing's being executed. We just get the warnings and we get a failure return code. This is super useful. There's one final note to be aware of. If you were to do bash -n on an empty file, it's valid. Because an empty file is a valid bash script technically. This isn't a quirk of bash. Other languages have this. Node, Node.js, JavaScript. I could give it dev null, -c is the equivalent of -n for bash, and it's the same thing. It considers that valid JavaScript. It's a valid Node program. So be mindful of that. Bash -n is great, but if there was something wrong, if you had this as some sort of like, CI or something, but the file was empty, it's going to return success. So be aware of that. Maybe check that there's something in the file before you actually syntax check it. So yeah, there's a hot tip for you. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to talk about signals and trapping signals specifically in bash. So what are signals? They're provided by your operating system. You might be familiar with some of these signals. You probably are if you don't even know it. Like when you control C a program, What happens? Well, there's actually a signal that your operating system sends to the program called sigint, the interrupt signal. When you kill a process, when you type kill and then some PID, you're sending it a signal. You're sending it sig term, the termination signal. When you kill -9 something, when you really want it to die, you're sending sig kill. This is one signal that can't be caught by your process. There's nothing your process can do about it. It has to just die. So yeah, those are provided by your operating system. You can trap them, you can manage them in Bash. You can do this in other languages, but I want to talk about Bash specifically. Bash also has a set of other signals, so I'll show you real quick. We have the trap command in Bash to react to signals, and there's a lot of stuff going on here, but there are some signals that aren't actually provided by your operating system, but in fact are provided by Bash. So on top of all the ones your operating system has, we have exit, which will get fired whenever your Bash script is about to exit, debug, which is executed before every simple command, return, which is executed each time a shell function returns. Like, there's a lot of cool stuff going on here that's even just like a lot of people don't even know about, but it's super useful in Bash. And then we have trap -L. So this is really cool. Trap -L will show you a list of all the signals. So we have all the basics. Like if you find 15, we're going to find sig term, 9 is sig kill. So here's all the signals we can trap, plus those other ones that I mentioned. So let's go into it. Let's go into our first example, simple exit. So what do we do here? We define a function called cleanup that just prints cleanup function running. And then this is the magic right here, trap. We run the trap command. It takes 2 arguments. The first argument is the code to run. And the second argument is the name of the signal that we want to trap. So the code to run, I've put it all into a nice little function here. And the signal is exit. So we're going to print some stuff, and then we're going to print some stuff, and we're going to see what happens. Let's go ahead and run this, and we get script starting, ... script done, and then finally cleanup function running. So the beauty of it is that this function will run no matter what. If we exit early for whatever reason, that function's still going to run. Unless there's something we can't do, like if someone kill -9s us, we're going to run this cleanup function. So that's beautiful. That's a way of getting something to run at the end. Let's talk about the exit code. Notice that we trap the cleanup function here. We put an exit code of 1 down here, but then we don't have an exit code up here. So what's going to happen? This is the beauty of it. When we run this, we still get the exit code of 1. So the cleanup function doesn't implicitly return anything, which is nice. We can define the exit code here. Super cool. Are we able to override the exit code? That was set to 1. It should be set to 2. Let's do this. So let's have exit 1 at the bottom and then exit 2 in the cleanup function. What happens when we run this? Yes, we can. So if you don't explicitly return anything, it will implicitly return whatever the script would have exited with. But in your cleanup function or the function that runs when you trap the exit signal, you can override the exit code. That is useful to know about. I don't know if you'd ever really want to do that, but that's up to you. Hey, I'm not programming for you. I personally wouldn't bother doing it. Once you're in the cleanup mode, like, there's really not much I can do. Like, you better exit quick. That's the way I view it. So what else can we do? Here's some magic. We can trap more signals. Let's trap debug. So again, trap the name of the code to run and then the signal. So the signal is debug. myfunc is what we're going to run. So myfunc is here. And we're going to do the exact same thing. Script starting, script done, exit 1. Now we're going to print debug running and then this variable bash command. So what happens when we run this? Look at that. We have debug anytime the program is going to run something. This is really cool. You can simulate this behavior. You may have seen something like this. If we go to the first example, we could run bash -x on the first example, and then you will see the plus sign every time we're executing a command. In fact, we get the plus sign in front of trap because, we haven't trapped it yet, which is pretty cool. I think, what is it? Is it PS4 is the variable? So we could change this to like debug that if we wanted to change what it looked like in front of all the commands. So here's a really cool way, bonus content here. Here's how you can debug your bash scripts. What else do we have? And then the final thing, this one's really cool. Let's trap a specific signal, sig info. Notice this line right here. Trap can fail. Why can trap fail? Well, your system might not have sig info. I'm running on a Mac. I believe FreeBSD has the signal. I encourage anyone watching this, if you're running on Linux, go try and run the script. It won't work. I don't think you'll have sig info over there. But yeah, we just sleep for 1 and then we echo the word running constantly. So if I go over here and run this, it will just echo running every 1 second. If I press Control T, I can send a sig info to my process and we'll see hello world appears. This is super useful. For all my Linux friends out here, you are missing out with siginfo. I love it. When I'm running a long DD command, I hit Control T and bam, it gives me information. Just like you would have to run SIGUSER1 to get it. I hit Control T and there's my information with DD. I love it. It's great. I've done the same thing on like a Linux system and sometimes I end up just borking DD. So there's a fun little trick for you, and that's signal handling in Bash. Yo, what's up everyone? My name's Dave and you suck at programming, and today we're going to talk about globstar in Bash. What is globstar? Well, you may have seen syntax like this, maybe if you're running on ZSH, I believe it supports it, and you can recursively glob into files and directories and find things that might be, 6, 7, 8 directories deep, N directories deep, and you try to do it on Bash, and you're like, well, Bash doesn't work. That's why Bash isn't as good as Z Shell. Well, let me slow you down. Slow down, all right? Relax. I'm going to show you how you can do it in Bash. So let's first of all, talk about where we are. We are in YSAP. This is the repository with all of my notes for all of my You Suck at Programming series. It's on GitHub. You can go check it out right now if you want to. The reason I'm in here is because there are a lot of files in here. I can prove there's a lot of files in here. I can find dot. And there's a list of all the files that are in here. It's a Git directory. The Git repo, so there's a bunch of stuff. But yeah, you can see there's a whole bunch of files in here. That's awesome. You could also do echo ***. And we just get a list of the root files. We don't get all of them. That's kind of interesting. I wish it would go into them. Well, guess what? Here we go. Let's turn on the globstar shell option. Shopt for shell option, -s for set, globstar, the name of the shell option. Run that, rerun this command, and there you go. There's every single file, and it's really, really hard to read them. That's because they're all being passed as an argument. Of course, we can separate arguments with new lines using this printf notation, ***, and there we go. There's our new line separated list of files. Now you might be saying, hey, I know this is a Git repo. Where do those Git files go? Well, we're not showing hidden files by default. They're hidden by default. Is there a shell option to turn them on? Of course there is. Same thing. Shop-s shell option set .glob. .glob now, we will suddenly get all of those hidden dot files up here. It just puts them in a different spot. There we go. There's all of them. So this is how you can have that behavior in Bash. So I could do like, ***, or let's do the printf notation. That's nicer. **/ based. And there are all my based scripts. Cringe. There are all my cringe scripts. So this is the behavior people are probably expecting. It does exist in Bash. You can turn them on. It's just hidden behind shell options. The beauty of all this is I could do something like text equals, I'm going to make a new array, and we're going to look for all of the text files, and we're going to store them in the array. Now we have a Bash array of all the text files. So we could, get the length of the array, and we can say there's 127 text files in here. We could do for file in this, do echo f, done. And, oh, no, we're counting it. Let me get rid of this pound sign right here. There we go. So now we have a Bash for loop that loops over every single text file we found without forking, execing external tools, just using Bash built in. So we could do whatever we wanted in this for loop. Super useful. That's globstar and .glob in Bash. Yo, what's up, everyone? My name's Dave, and you suck at programming. And today, I'm going to demystify if statements in Bash. Sounds kind of weird, right? But you ever notice that there's the test command, there's a single square bracket, there are double square brackets, sometimes there's 2 open parentheses. What's going on here? Let's jump into it. Let's break it down. All right, so what do we have here? We have a lot of test scripts. Let's jump into it. Let's jump into the first script, simple test. If test -f foo.jpg, then we print foo.jpg exists. Let's go ahead and run that, and we get foo.jpg exists. As you can see, foo.jpg does exist, so that looks really good. As you can see, the test command, what did it do? It tested that it was -f. This means test to see that it's a file. There are a whole bunch of things you can test for. We can run man test, and there'll be a whole list of things that we can do here, right? I'll get to this in a second, but yes, most of these should work, but we'll dive into it. There's a lot to talk about. Let's move on to the next script, which is the simple bracket. Same exact thing, -f, but we're using a single bracket. Will this work? Yeah, it'll work. It's the same exact thing, right? And then let's talk about this one. We have the double square bracket. Will this one work? Of course it will. So they're all exactly the same, right? Not quite. Let's talk about it. First things first, what is test? Let's do which tests. It exists in our file system, but we're in Bash. Type -a test. Test is a shell built in. test is also /bin/test. So test is built into bash, but there is also a command that exists on your system called test. It's POSIX, it has to be there. But test is built into your shell. Because it's built in, we don't need the man page, we need the help page. This is how we view man pages for built-in commands in bash. Help test, here's everything we can do with test. So here's every possible operation. As you can see, we were using -f, which is true if the file exists and is a regular file. There's a whole bunch of other stuff we can do here. We have equal, not equal, less than, greater than. We have all sorts of fun stuff that we can do with that. We also have help single bracket. That is built into bash. This is a synonym for the test built in, but the last argument must be a literal closing brace. So to answer people's questions, first and foremost, test is the same as the open and close square brackets. They are the same. They are so much the same that this will exist on your file system. I'm not joking. This is an actual command on your file system. You can execute it. You could quote it if you want to, and we could say -f foo.jpg, close that bracket, and it returns 0 because it exists. That I'm not lying to you. That really does exist on your machine. A little bit gnarly when people first find it out. I would invite you to go actually look into the source code for some of these things, because a lot of times test and open square bracket are the same program. There's just a nice little pound defined at the top that figures out how they're being compiled. You actually pass a compiler flag. I'd have to double check. Whatever. They're the same program effectively. The square bracket just requires the closing square bracket. So let's talk about some fun stuff going on here. Let's look at the next script here. We're having a bit of a deep dive here. We're going to use the double square brackets. The double square brackets are specific to bash. They are built into bash. There is nothing on your file system that can do this. This is only built into bash. So when you use double square brackets, you're saying, I definitely want the bash version of this. We get some more features than just the test command or the single square brackets. So let's define a variable. F is test.jpg. And then we're going to check, does test.jpg equal star.jpg? $f is a JPEG file, $f is not a JPEG file. What do you think is going to happen? Are we going to match it? I mean, it's a star here. Are we going to expand that glob? Let's run it. Test.jpg is a JPEG file, meaning that this was true. So this is equal to star.jpg. Notice that the double square brackets allow you to do patterns. The next script is called pattern fail because it's the exact same script, but we're using single square brackets. So this is the more POSIX-y version. As you can see, we get an error here. It doesn't work. We get too many arguments. There's too much stuff going on here. The reason we get too many arguments is because this is actually being expanded to all of the JPEGs in your current directory. So be careful with this. So yeah, that's why that one fails. So when I'm in bash, I prefer to stick to the double square bracket, but there are some gotchas you should know about. What do I mean there's some gotchas you should know about? Let's talk about it. How do we not do pattern checking? Well, it's bash. We just quote it. Quote your right-hand side argument, and this will stop it from doing like globbing or pattern or wildcard matching. If you quote it, it will check for literally being that. So when we run this, we can see test.jpg is not literally star.jpg, which is good. It shouldn't be. It should fail that if statement and we should get here. That's what happens. That's awesome. So then you might be wondering, well, wait, what else is there? Well, we have numbers here, right? So we have a equal to 9, b equal to 10. Let's check if b is greater than a, then we'll print b is greater than a. Otherwise, we'll print, uh-oh. So let's look at this. B is 10 and a is 9. So 10 is greater than 9, right? Let's go ahead and run that. Uh-oh. I'm just laughing that I put uh-oh there. So what's going on? You might already know what's going on, but let's jump into it. We have to use this syntax. This is the more POSIX style, like the test syntax, -GT for greater than, because this will work. And I'm spoiling that, but yeah, you can see 10 is greater than 9. So why does that work? Well, let's pull up the help page for square brackets, and there's going to be a whole bunch of stuff here. In fact, a lot of them are inherited from tests. So let's pull up that and let's go here. String less than, string greater than. True if string 1 sorts after string 2 lexicographically. So it's doing basically alphabetical sort lexicographically. I think that's how you pronounce it. So what's happening here is we're treating them as strings, and the string 1 sorts before the string 9. We're not sorting them numerically. We're not comparing them numerically. We're comparing them like strings. So that's a gotcha to watch out for. Even though I told you to stick with the bash syntax, you can still run into issues. So how do we fix it? Well, you use that -gt, like I showed you. This will fix it. Or what I like to do, get ready for this. This is real syntax. I'm not lying to you. We can use open parens. Double open paren, double close paren. This is arithmetic expression. This is specific to bash. Only bash can do this, but now this will treat them like numbers, and this means we don't need the dollar signs in front of them. They'll get expanded automatically. We can use all sorts of numeric comparisons here. You run this, and it just works. You can do help on open parens like this, and you get the help message, and you will see that it's equivalent to let. So this takes whatever let takes, so we can do help on let. And here's a list of all of the things we can do. Look, we have post increment, we have pre-increment, we have exponential, we have modular division, we can do bit shifts, logical, bitwise operations. There's even a little like ternary thing in here. There's a lot you can do with bash math. It is pretty cool. So yeah, hopefully that demystified all this stuff for you. Yo, what's up everyone? My name's Dave and you suck at programming. And today we're going to be talking about bash. Of course, we always do. We're going to talk specifically about looping in bash and when you can use the continue and the break keywords, because in bash, this is really cool. Some other languages have this too. You can give them an optional argument. The argument is a number and it's how many levels you want to break out or continue, which is really cool. I wasn't aware of this. A chatter actually shows me, one of my viewers shows me, I don't remember who, so apologies for forgetting who you were, but you are awesome. Thank you. Shout outs for showing me this. We have a bunch of stuff going on here, so let's look at our first simple example. This is just nested for loop, basic nested for loop in bash. We're going to loop over 0 through 2 inclusively. We're going to loop over A through C inclusively, and we're going to print them. So we're basically just making a combination of the two. So when we run this, we get 9 outputs, 0 ABC, 1 ABC, 2 ABC. Very simple, no trickery going on here. Let's look at the first example. If I is equal to 1, and if j is equal to b, so the halfway point for both of these, then we will continue, otherwise we'll print it. So if you know what the continue keyword does, it says go back to the top of the loop and start processing the next element. So if we run this, all we should do is skip 1b. And that's what happens here. We get 3 here, we get 3 here, but we only get 2 here. We've skipped 1b because we very explicitly called it out. Let's look at our next example. It's the exact same logic. We have 1 and b here, but we're calling break instead of continue. If you know break doesn't go to the top of the loop, it breaks out of the loop, so it goes all the way below it. So what should happen here is once we get to 1b, we don't print it, and we actually stop processing all the ones completely. So, like I said, we have 3 up here, 3 here, and we have 1a. We don't have 1b, and we don't have 1c. We've stopped completely. So a lot of setup here. Let's talk about continue n. So same thing, we're looking at 1b, but we're going to continue 2. So we're not going to go up to the top of this loop. We're going to go to the top of this loop. That's functionally the same as breaking 1 level, so the output should look very similar to the command before it. And it does. We have 3 up here, 3 here, but we only have 1 here. What about when we break n? This one's really cool. We're going to break out of 2 levels. So instead of breaking out of this loop, we're going to break out of this loop too when we hit 1b. So let's go ahead and run that. And what do we get? We completely stop processing once we hit 1b. These are very contrived examples, I know, but you've ever been in a situation where you're like nested very deeply, you're in like 3 or 4 loops and you got to break out of a couple of them. Probably refactor it and put it into functions. I'm just being honest, but sometimes it's useful to have this kind of logic and to have this trick up your sleeve. The last example I have here is a function. This is what I like to do. I would never have a function that was like nested like this, but regardless, the point of this is that once you're in a function, you get access to the third keyword. You had continue, you had break. Now you have return. Return is a very nice keyword to just break out of the function. So if you can break these nested loops into smaller loops, put them into their own functions, then we have the return keyword so we can simulate a break and a continue. So this is how to effectively accomplish what I showed you before, but still, it's cool to have those tricks up your sleeve. It's cool to know that break and continue take an optional n argument, and you can see that in their help messages because these are both built into the shell. And yeah, that's it. Hopefully you learned something. Yo, what's up everyone? My name's Dave and you suck at programming, and today I'm going to show you some simple quality of life changes you can use in your bash shell right now today. Super easy to enable. This is a trick when it comes to CDing around to make your life a little bit better. I know there are tools out there that people use that are like CD replacements. They do all sorts of fancy things. If you're like me, you like to keep things fairly minimal but maybe throw in a feature or two, Here is an example of that feature or two you can enable right now on your shell. So the first thing we're going to talk about is cd spell. So if you use shopt shell opt, you can do shopt cd spell and it will tell you if it's on or off. I have it on right now. You can turn it on with -s. You can remember that as set. We set it on. You can turn it off for whatever reason with -u. I spelled it wrong. -u for unset in case you wanted to turn it off. But in our example, we're going to turn it on. So I run this. This only works when you're interactive on the terminal, but check this out. Let's take a look. Let's go to my home directory. All right. Let's ls, and we have a whole bunch of directories here. Let's cd into my dev directory, dve. Uh-oh, we spelled it wrong. What's going to happen? It works. Look at that. It printed the correct spelling, and what did it do? It brought us in there. That's amazing. So cd spell is a super simple thing you can turn on your shell right now. It only works interactively. You don't want to use it in scripts. I wouldn't recommend you use it in scripts. But the idea is that it can fix simple spelling mistakes. It's not perfect, but it can get around just simple little typos. If you know me, I have aliases for things like chommed, and I have aliases for suad, the irony of me misspelling alias right there and having to fix it. So I love things that fix my spelling when I'm working interactively. All right, so the next shell option I want to talk about is auto cd. So check this out. We have this. This is super useful if you're in a situation like, I'm in my, let's go to my home directory. Let's do dev/bash course. Maybe I want to work on my little bash course that's coming up and I forget to put cd there. Don't worry. Auto cd will run cd on your behalf. So this is super useful. Sometimes I'm just like hunting around trying to find the file I want. I'm like, it'd be easier if I was just in this directory. I can just hit enter. I don't have to go back to the beginning of the line, put cd there. Auto cd will do that for me. Just like cd spell, it only works when you're interactive on the terminal. So don't use this in a script. I don't think you should ever use this in a script, to be honest, but interactively on the terminal, it's a super useful trick. They do not work in conjunction with each other. Okay. So if you spell it wrong and you also forget the cd, you're out of luck there. Okay. If I just do this, it doesn't know what I want, okay? But between the two of them, it's super useful, and it kind of helps you out of annoying situations, and I absolutely rely on ... I use ... so much to go up a directory instead of having to do cd ... It's just a small little quality of life change. I just sometimes do this when I'm trying to get back to the root directory if I'm like lazy, and instead of just doing that, I just do and I'm like, yeah, cool, easy, good to go. So yeah, that's it. Yo, what's up, everyone? My name's Dave, and you suck at programming. Today, we're going to demystify here docs, specifically in bash. I think other shells have this too, but have you ever seen syntax like this? When you run a command like cat, or you look in a script that has this, and you'll see one less than sign. Okay, we're going to read in from a file. That's great. But then you see two less than signs, and maybe EOF or some string like that, or two less than signs and then a hyphen and then EOF, or sometimes there's EOF and it's in quotes, and you're like, okay, I know something's going on here. What's going on? That is called a here doc. This is the word I'm saying. Here doc is what they are called. So yeah, let's jump into it. We have a bunch of scripts here. Let's jump into the first one here, simple. So here is the most simple example of a here doc. Take a look. We have cat reads in less than until EOF, and then we have EOF right here. So what's happening? Bash has this notation of less than, and then you give it a marker string EOF here, and whatever text is here will get passed to cat over its standard input. And cat, very simple program, reads in from standard in and writes the standard out. So if all things work as we expect, this should show up on our terminal. Hey, look at that. That's super simple, works exactly how we want it to. In this example, we have a couple spaces at the beginning. Those spaces are retained. Hey, that's amazing. Let's look at our next example called indent. Can you see where I'm going with this? Let's say we have a function. We have a function here called main, and we have cat in here, EOF. We have hello world with that indentation. And then notice EOF shows up here. If I put it over here, fails, doesn't work. It has to be on the beginning of the line, okay? So let's go ahead and run this example. Look at that. Now it's moved over by a whole tab character because I indented it with tabs. So it retains the white space even when you're in multiple levels of indentation. So is there anything we can do to fix that indentation? Well, let's take a look at fix indent and see. Hey, look at this. We have the exact same syntax, but you see this character right here that I'm hovering over? The hyphen, that's what that does. So we have less than hyphen. Hyphen just tells it to ignore the leading indentation. So it's super useful. We can put it in little functions like this. And notice it still retains the spaces. It just got rid of those tab characters there. So it's pretty smart when it comes to that. You can get into some weird situations with it. But yeah, this is super useful. We can also put EOF at the same level of indentation as our cat invocation, which is super nice. We don't have to put it at the beginning of the line. So that's super nice. Great for like usage messages if you're inside a function or whatever. Let's take a look at this next example called variables. We set foo equal to 1 here, and then we run cat. We're using the hyphen, though it doesn't matter. We're not at any sort of level of indentation. And in here we say hello $user. This is all capital. This is built into bash. This should resolve to the current executing user's name. Foo is $foo. The uname command says uname. Look at that. We're using command substitution in here. So what do you think is going to happen? The syntax highlighting is kind of giving it away, but let's take a look. We run this and it all works how we expect it. Hello, Dave. Foo is 1. The uname command says Darwin. Hey, that's awesome. That lines up with what I would expect to happen there. So what about this next example called no variables? What's going on here? It's the exact same code, but look at this. We have quotes around EOF. EOF is quoted. Notice down here, the quotes are gone. The quotes are special. The quotes say whatever goes in this here doc is literal. Don't try to do any sort of processing it on it at all. So we have $user there, $foo. We have the command substitution. Let's go ahead and run this, and we get the literal string. So quoting the EOF marker in here docs will make it so it doesn't undergo variable expansion, all sorts of like splitting, stuff like that. So in our next example, we have something called any EOF. What does that mean? Look at this. We changed EOF for anything underbar LOL. It can really be anything. There's some weird exceptions to this, but for the most part, it can be anything. So we run this example. I'm not tricking you. It works exactly how we think it should work. Hey, that's pretty cool. Example number 6 here, we have not just cat. You can use other commands. We're using cat because it's a very simple command, but you could use grep, you could use whatever you want. In this example, we have echo. And let's look at this example. We echo foo. Foo also reads in from standard in and says bar. Cool, right? Let's go ahead and run that. Let me type the right thing. Okay, there we go. And all we get is foo. We don't get bar. When I said echo reads in from standard in, I was actually lying. Echo does not read from standard in. It's being passed this over standard in, but echo does not look at standard in. Echo takes arguments and echoes them. It does not read standard in. Cat reads from standard in. A bunch of programs do. Echo does not. So that bar is lost. That bar is completely gone. We don't see it anywhere. So in our next example, you can pipe this. My syntax highlighter doesn't like it, but it works. We're going to cat whatever comes in here. Cat's going to pipe this to NL, which will give it line numbers. We're going to grep for the word bar, which should match because it's right there. And then we're going to pipe it to tal, which again won't really do much. This is just to show that the pipeline will work how we expect it. And there we go. We can see the first line was bar. We could prove this. We could do foo, bar, baz. So because we're grepping for bar, it should find the second line. So that number should change from 1 to 2. And there we go. Hey, it works how we expect it to. The last example I have right here is called who wins. So here's an interesting example. Echo foo, pipe it into cat. So cat should print foo, right? Well, we also have a here doc here. Cat's going to read bar on its standard input, but we're also passing foo over standard in. We can't have two standard inputs, so what's going to happen here? What's going to print? Are we going to get foo? Are we going to get bar? Are we going to get a weird combination of the two? Are we going to get yelled at? Let's find out. The answer's super underwhelming. It's just bar. So let me, here, I'll pull up both so you can see both at the same time. As you can see, the here doc won. The echo foo here, that was lost. That's completely gone. The here doc won. That is just how bash works. In fact, if you were to use a tool like shell check, which will do static analysis of your scripts, you can see that it even yells at you. Look at this. This redirection overrides piped input to use both merge or pass file names. So it even says this redirection overrides piped input. So that's what's going on there. Can't do anything about that. And yeah, this has been a crash course in here docs and bash. Yo, what's up, everyone? My name's Dave, and you suck at programming. Today, we're going to talk about here strings in bash. Now, you might be thinking, what is that? I have no idea what that is. You know when you see something like this where it's cat and then the name of the file because you have one less than sign there? Hey, that's awesome. We can do redirection in bash. You ever see the two less than signs? Hey, we can do the same thing. We can pipe into the standard input of cat, but this time we can put whatever we want here, put EOF, and then we get whatever I put there. Hey, that's pretty awesome. Did you know there's an alternative syntax? So instead of that, we can just, cat with 3 less thans. Hey, that's awesome. What do we put here? A string, LOL. So instead of reading from a file or reading until EOF, we read from a string. We use 3 less thans. That is called a here string. Let's look at some of the examples we have here. The first example, the simple example, it's exactly what I just showed you, just to show that there's no trickery going on here. Hey, it does exactly what we want. Let's look at the first example now, 01 from var. So we have a variable here called input, and we say this is a variable for $user. Okay, $user will expand to our current username, so in my case it'll be Dave, and then we put that into cat. So cat will receive that as standard input, and this works exactly how we expect it to work. Hey, that's awesome. Let's look at our next one. We have something called read example. we're going to use the read built-in. I'm not going to go into the specifics of that. We're going to read this string foo space bar space baz, and we're going to have 3 variables here, A, B, and C. We're going to read that into A, B, and C. We'll get A is A, B is B, and C is C. So here's the script. If we run that script, look at that. A is foo, B is bar, C is baz. This is a way of splitting strings in bash using the read built-in. Super useful, and also shows how the here string can be used to do that. What's the next one? So we have, what is it called? Into func? That's not right. Into func. Okay, so what's going on here? We declared a function. This function does a while read line. That means it continuously consumes standard in. We're not doing any sort of redirection here. We don't have the name of file here or anything. Nope. We're just going to read from standard input, and the standard input of a function is right here. So we're going to read this in. So if we run that, here's what the source code looks like. If we run that, we can see that we got 1 line. This is 1 line. Of course we got 1 line. We only passed it 1 line. Hey, that makes perfect sense. We can also pass in multi-line. So this is a bash syntax to expand special characters. The special character in this case is the new line. So you can see this is new line, 2 lines. So what happens when we run that? Take a look at this. We got 2 lines. So even though it's in a string, you can pass multiple lines in there because the string can just have a new line character in it. This is a super useful way of passing strings as standard input into a function or a command or something without having to use like echo or cat or anything. This is completely built into the shell. Super simple, easy redirection. This is here strings in bash. Yo, what's up everyone? My name's Dave and you suck at programming. Today, we're going to talk about tilde expansion in bash. This works in other shells. I'm going to talk about bash specifically. I'm sure a bunch of these concepts still apply. It's surprisingly complicated. There's some weird gotchas with it. And I'm going to show how to deal with it, okay? So what am I talking about? I'm talking about this character, the tilde character. When you run this in bash, echo tilde, it should just echo whatever's going to the screen. It gives me users Dave. That is my home directory. Super useful. You can use that. You've probably seen this a bunch of times on the shell. You can quote it. If I put quotes around it, it won't expand it. So bash is responsible for turning that into my home directory, the literal string of my home directory. You can quote it to avoid doing that. You can also use double quotes. So some people get tripped up here. They think it will expand in double quotes. It will not, okay? The ordering happens a little bit differently than you might think. But what can we do with this? Because this is super useful. I can give it things that are in my home directory. Like I happen to know that I have a directory there called dev. That's where I do my dev work. But you know what I don't have? I don't have a directory called does not exist. But it still gives it to me. Here's the thing about tilde expansion. The tilde expansion just turns this in your home directory. This is just a string that got tacked onto it. We concatenated these strings together. So there's no file system check for this file. Yeah, this file doesn't exist, but nothing checked that from bash's point of view. It's just a string. If I stat it, you can see no such file directory. That makes sense. But did you know there's more that you can do with this? There are a couple weird ones that people don't really know about. Let's go and cd into my home directory. Let's cd to temp. And now we can run pwd, and you can see that we're in temp. Hey, that's awesome. You can also run tilde plus. Look at that. Still says temp. That's our current working directory. You can run tilde minus, and it has my home directory. That was my previous directory. So the first one, tilde plus, that is pwd, and the tilde minus, that is old pwd, if it is set. Pretty cool. I never really used these, but they're kind of cool. They were in the bash man page. That was fun learning about them. We can also do some other cool stuff with this. Tilde Dave. That's the home directory of Dave. Tilde nobody. That's the home directory of the nobody user on my system. Tilde root. That's the home directory of root. Tilde John. John doesn't exist on my system, so we just got the literal string tilde John. So you can use this to get the path of someone's home directory. Just be careful because error checking it, there's no real way to tell if there's an error. The only thing you can do is look at the string you gave it, check the string it gave back and see if they're the same, and then you can assert that there most likely was an error during that. We can also use this in variable declaration because bash says we're allowed to use it at the beginning of a variable. If we have this like hi, and then we echo $foo, we can see that it has my home directory in there, but only at the beginning of a variable. If I have hi/tilde, we just get the literal tilde character. Bash is a little bit weird about this. Not weird, it's actually well defined. It says that it can come at the beginning of the variable or the beginning of a colon in the variable. So if I have this, and then I have colon/foo, and then I have colon tilde again, we can go ahead and we can echo that to the screen, and you will see it's resolved my home directory twice. This is useful if you've ever modified variables like path this on your machine will tell it the path of where all your executables are. They're separated by colons, and this is why it's useful for that, because you can make a path variable and it will expand the tildes after the colon, because this is just common. This is just something you see a lot. Here they are separated by new lines, a lot easier to read that way. But this is useful if I want to do like path equals, bin, colon, sbin. I could do something like that. I'm not going to run that. That'll make things a little bit weird over here, but that's why it works that way. And the gotcha to watch out for here is take a look at this. Let's say name equals Dave. We know that exists on the system. If we do this, what do you think is going to happen? Doesn't work. Now, you might think, Dave, I'm smart. I watch your content a lot. I know to quote my expansions. Well, we know quoting the tilde won't work, but you're like, Dave, I've watched your stuff enough. I know to quote just the variable expansion and run this. They don't run in the same order as you want them to. Okay, that's the problem here. So this is just not going to work how you expect. This will work just fine. We'll just get Dave after my home directory, but this won't work. Tilde expansion and variable expansion are separate, so you can't do something like this. You could cheat the system. You could run this whole thing through eval, and this will work, but of course it's eval, so be careful with this. There's a lot of weird gotchas. I know the name Dave is safe, but what if I had unsafe characters in there, semicolons, things like that? It can get gnarly pretty quick. There's probably safe ways to do it. I don't know. My only question would be is, why are you trying to determine the path of someone else's home directory? Maybe rethink your process structure at that point when you're like programming something like, why would you need that information? Not in a judging way, but if you're running like an install script for someone, maybe they should be the one running that, and then it's as simple as getting their home directory. So yeah, there's a little tilde deep dive in Bash for you. Yo, what's up, everyone? My name's Dave, and you suck at programming. I got a quick one for you today, okay? We're going to talk about dev null. This is a special device. It's on Unix systems. You've probably seen it. You've probably used it. You probably know it can be a little bit dangerous because you can accidentally delete files if you're not careful. Let's talk about it. Really simple. So let's jump in here. We have a couple scripts. Let's look at our first script here. Cat dev null. Hey, no trickery there. It's a file, so let's go ahead and cat it, right? What happens? We get nothing. We successfully get nothing. We were able to open that file, read that file, and close that file. There's just nothing in there. It's a special device that exists in your system that you can open, you can treat like a normal file, and that's great, but there's nothing in it. It's completely empty. That's why it's called null. So what's the next thing we can do here? We can, instead of using cat, wow, I'm just typing all wrong today. Instead of using cat, we can use bash built-ins. We can read in from this file, we can do a while read line, and we can echo line. This would normally read a file line by line. So what happens if we run it like this? No trickery. It does exactly what I said it would do. It will successfully open the file, the loop will run 0 times, it will have nothing to print, and we're done. Super simple. What's the last example here? We have is a file. This one's important. Let's look at this one. In bash, we can say -f, and then the name of a file, and this is a way to test, is it a file? So dev null is a file, dev null is not a file. What do you think is going to happen when we run this? Dev null is not a file. That's interesting. We're treating it like a file, right? If we ls dev, wow, I did not expect that output. Let's stat it instead. Let's stat dev null and see what's going on there. I'm on my Mac. That's the Mac style stat. Let's use gstat instead. This is the GNU stat. You're probably more used to this if you're on Linux. So we can see right here, what kind of file is it? Character special file. It is not a regular file. It's a character special device. This is provided by your operating system. So it looks like a file. It acts like a file, but there are some subtle differences with it. But we can treat it like a file, which is pretty cool. I can cp dev null into file.txt. Now I have a file in my directory called file.txt. You know what's inside it? Nothing. It's an empty file. I just copied an empty file. It's no different than copying any sort of empty file that exists anywhere, and dev null is still there. Here's something that doesn't work though. I sometimes get comments like this and people say, oh, you could just move it to dev null. Let's talk about that. Move file to dev null. What do you think is going to happen? Here's the thing. Dev null is not a directory. I'm going to get an error. I can't move it there. It's not even an e-access. E-access would be access denied, like maybe with sudo you could possibly do it. This is operation not permitted. This is eperm. This error doesn't mean that you didn't have the ability to do it. It means no one has the ability to do it. This can't be done. You can't move something to dev null. It's not a directory. I can't overwrite it. There's nothing I can do. The system's not saying, oh, you don't have enough access. The system's saying, no, this is logically impossible what you're asking me to do. There's no way I can satisfy this. So sometimes I get comments, people are like, oh, you could just like, rsync it to dev null. And it's like, try it, see what happens. So yeah, there's your quick deep dive into rsync. So yeah, there's a quick deep dive into DevNull. Yo, what's up everyone? My name's Dave and you suck at programming. Today, we're going to talk about process substitution versus command substitution, specifically for the bash shell. I'm sure some of these concepts apply for other shells, but we're going to talk about bash specifically today. So let's jump into it. Let's talk about what am I actually talking about. So in this simple example here, we have name equals backtick whoami backtick. This is a little contrived. There are other ways to get your current username, but here's what we're doing. Name equals backtick whoami backtick. So we echo $name. It should be the output of that command. The command is whoami. We run it and it just says Dave. That's awesome. If I run whoami, the command right here, we get Dave. So that's all it did. This syntax is super simple. It says run this command and replace it with whatever the standard output of that command was. So name, the variable, got set to whatever the standard output of whoami was. Very simple. You've probably seen that before. And if you've seen that, you've probably seen this syntax. Instead of using the backticks, you can use the $ open paren and close paren. This is a newer syntax. When I say newer, I still mean it's decades old at this point, but it's newer. It is, I believe it is POSIX compatible now. But yeah, so use this syntax, prefer this syntax. It should work exactly the same, but the beauty of this syntax is when you start nesting things, there are way better rules for having nested this syntax where it's like this than having like nested backticks. You have to escape things, blah, blah, blah. I'm meandering. You run this script, we should get exactly the same thing. Hey, that's awesome. So what's the next thing? We have command args here. So in this example, I'm doing printf %s with a new line, and I have a less than and greater than. There's nothing special about those less than and greater than. That is just for us to see, and we're going to give it the uptime command. So if you've never seen the uptime command, it's pretty useful. It tells you how long your system's been up. It's a way to get load averages and stuff like that. You can see there's a bunch of data there separated by spaces. So what happens when we run that? We get everything, okay? So command substitution gave us that string back, but I'll show you what the script looks like so you can reference it at the same time. So it ran the command, got the output, and then the output was passed into this format specifier, which gets repeated for each argument. So each argument was being passed to printf like this. And you might think, okay, well, how do I avoid this situation? Of course, it's very simple. Just quote it. Quote your expansion. No different than you would quote a variable expansion. You put quotes around this thing, and now when you run it, we get one big argument with all of the data that was the output of that one command. Hey, simple. That makes perfect sense. That's called command substitution. We use that syntax, command substitution, to run the command and replace it with the standard out of that command. So the whole command has to run. We get all of the standard out. So what goes on here? Notice instead of the $, we have that less than sign. This is called process substitution. So we're using uname instead. So the uname command is just going to print Darwin, super simple. We're going to run this and it's going to echo it. Remember that? What is going on there? I'll show you the code so you can cross-reference it. We're echoing uname, but we got this. What is that? That's not the output of uname. And that's the thing. It's not the output of uname. Take a look at this. Instead of echo, let's do cat. Cat's going to get that weird thing, that dev fd or whatever it was, and now we get Darwin. So what's going on there? This is not getting replaced by the standard out of uname. It's getting replaced by the name of a file that cat will get, that if cat reads that file, it will get the streaming output of the uname command. I mean, technically it might be a pipe. I don't actually know what type of file it is. You know what, now that I say that out loud, let's actually find out what kind of file it is. Because if I echo uname, it gives us the name of the file. I could actually just gstat it, and where do we have it? It is a FIFO. Look at this, FIFO. So it is a pipe, it's not a regular file. Okay, let's get back on track here. So we ran that example, we get the output of it. It gets replaced by a file name, which happens to be a FIFO, which is a named pipe that exists on your system. Cat can read that file, and that file will get replaced by the standard out of the command that's being run in that syntax. Why is that useful? Because what if we have large data? So here's an example of large data. We're going to grep for the name Dave out of user share dict words. That is a word dictionary that exists on my system. You may or may not have it on your system. It has 235,000 lines of words in there. So it's a large file. We're going to grep for the word Dave in it, and we're going to loop over it line by line using this here string notation. So all of this stuff, all of the output of grep is stored in a variable that has new lines in it, and we're going to loop over that variable and find where it says Dave. So let's go ahead and run this. Okay, it ran pretty fast, but there was like a little bit of a pause there. It had to cache the whole thing in memory. It had to store the whole thing in memory before we looped over it line by line. Let's talk about, by contrast, why process substitution is useful. Look at this example. We have this, a little bit contrived of an example, but take a look at this. We're going to tell it to read in from a file. What's the name of the file we're reading from? This, because remember, that will be a FIFO, and that will have the output of this command in a streaming fashion. So the benefit of that is it will flood in as it becomes available. There wasn't much here. Even though it's a relatively big file, it's still pretty fast for computers to chug through this. But this is super useful. That's the difference between command and process substitution. So if I show the two examples again, let's do 06 and 07. This is great. This command substitution is great when you can fit the whole thing in a variable comfortably. The whole thing's going to be read into memory and you're not worried about it. This is also useful because I can get the exit code of grep. When this next line moves on, I know that grep has finished. By contrast, if I go over here, I can stream a lot of data. Maybe I have a tail -f that's running, or I'm curling some sort of interface where I don't know how much data is there. That's the beauty of this. I can start processing input before the command's done. Because I'm processing input before the command's done, we don't have an exit code. I can't tell you if grep was successful or not until it's done, and we're processing lines before it may be done. So that's why you got to pick one over the other. You got to pick which one makes sense. If you can fit the whole thing comfortably into memory, command substitution is probably for you. If you want to have something in a streaming fashion, you don't care about the exit code, or you have ways of dealing with it yourself, process substitution is the way to go. That's the difference between the two. Yo, what's up, everyone? My name's Dave, and you suck at programming. Today, we're going to talk about why this one character is the bane of my existence when I'm dealing with Bash, okay? And what prompted this video is I get a lot of people talking about, using AI to generate Bash, or they have LLMs do something. LLMs are really good at showing this one syntax that is just wrong. It works, but it may not work. I'll show you what I mean. I'll show you why it's a headache, okay? Because I've seen this code enough and I'm sick of it. Before we talk about that, let's talk about the actual principle under here that we're going to be talking about, which is parameter expansion. So here's a simple bash script. We say foo equals hello world. We're declaring a variable, no trickery there. And then we can use this beautiful syntax to set a new variable called bar. Bar will be set to whatever foo is set to, but we're going to replace every instance of hello with goodbye. Actually, no, we're going to replace the first and only instance of hello with goodbye. If we had 2 slashes here, it would be every instance, but we only have 1 slash, so we're going to replace hello with goodbye. No trickery there. We're going to echo what foo is. We're going to echo what bar is. We should get hello world and goodbye world. Look at that. I'm even telling you what we should get before we run it. And hey, our system is saying that makes sense. That's what we want. So what's the issue here? Let's talk about some HTML, okay? You may have seen something like this when it comes to encoding something for HTML. When you have HTML documents, less than signs mean something, greater than signs mean something, ampersands mean something. So let's talk about that. Imagine a string like this. Dave likes Bash and Unix. We have less than, we have greater than, we have ampersands in there. If we want to make this safe for HTML, we have to escape some things. There'd be more than this. This is non-exhaustive. This is just an example. But we have our enc. This is for encoded string, and we have our raw string. So ENC is for encoded. So we have our raw here. We're going to replace 2 slashes. So we're going to replace every less than sign that we encounter with ampersand LT semicolon. Okay, makes sense. Then we're going to reread that string and replace every single greater than with ampersand GT. Cool. And then we're going to replace every single ampersand with the ampersand symbol itself and then amp semicolon. So what happens when we run this script? Let's go ahead and run it. And what do we get? What's the name of it? There we go. So we have our raw string looks like this. Okay, that makes sense. Dave likes the less than sign is still there, but instead of an ampersand, we just have this, but the less than sign is still there. The greater than sign is still there. This looks right. The less than sign is here. So this is wrong. Something's clearly wrong here. Let's talk about it. So I just realized I somehow lost the O2 script. I'm going to go ahead and write that real quick, and we'll just edit this part out. All right, so let's take a look at this next script here that we have and has been here totally the whole time. Didn't just pop into existence. We have O2 what here. So we have a slightly different string. We have Dave likes Bash and Unix, AND, no ampersand there. And we're going to change the word and for the ampersand, okay? So we're going to, again, print the raw string and the encoded string. So let's go ahead and run that. And what do we get? We get the same thing. Why do we get the same thing? That seems super weird. Shouldn't we be changing the word and with the literal ampersand? Well, let me go ahead and visualize this for you in our next script. Visualized. So let's change and, which we have right here, with hyphen, hyphen, ampersand, hyphen, hyphen. Just literal hyphens, no big trickery going on there. We run this, and look at that. We have hyphen, hyphen, the word and hyphen, hyphen. That's because this character is special in Bash, okay? Bash takes whatever was matched here and you can back reference it effectively. You can replace this with what was matched with the ampersand character. And a lot of people that give me, AI generated code, they don't seem to know this. The LLMs don't seem to quite understand this. If you talk with them a little bit, they seem to pick up on it, but yeah, this is a problem. So what can we do about this? We can fix it. And the way we fix it is very simple. We just escape the ampersand. You could technically also quote it, but we're just going to escape it here. And that's the only difference here. We just put a backslash in front of it to escape it. We go ahead and run that. And hey, look, that's awesome. We have a literal ampersand without anything going on. That was the change we made there to fix it. So what's the next one we have? We have HTML almost. And this is our first example with the HTML where we're going to change the less than with a escaped ampersand, escaped ampersand, and escaped ampersand at the end. So let's go ahead and run that one. This one's called almost. Why is it called almost? Because look at that. We have an ampersand. No, we're supposed to have a less than there. We have an ampersand and then a less than. It's almost like there was an ampersand here and then we double encoded that ampersand. Is that what happens? Yes, that's exactly what happens. So how do we fix it? Super simple. We just change the order, okay? So we do the amp encoding first. We encode the ampersands first, and then when that happens, then we can safely encode everything else because we're using the ampersand character, which we already had to encode. So if we do that in this order, now we have a non-exhaustive HTML escape function. We still technically have to escape quotes and stuff like that, whatever. But look at this. We have ampersand less than, ampersand greater than, the actual ampersand here, less than, greater than. That's super useful. For some reason, LLMs seem to miss that you have to escape or quote this. So that's super fun. It's a little pet peeve of mine. But this is super useful. When you match things in parameter expansion, you can use that string later with an ampersand. So when an ampersand has a special meaning in Bash and it also has a special meaning in HTML, it can get really hard to tease these things apart. So hopefully this helped you. Yo, what's up, everyone? My name's Dave and you suck at programming. Today, we're going to talk about a hotly requested item, okay? We're going to talk about permissions on Unix file systems, but specifically permissions around directories. Because a lot of people had questions about this. They were like, Dave, what happens if you like take away execute permission, but you have read permission on a directory? Doesn't that seem kind of weird? And it's like, well, yeah, I mean, that is kind of weird, but let's talk about it. Let's see what happens. And maybe some operating systems are different than others. So for this example, we're going to be on Linux here just to kind of keep some things consistent, but let's go ahead and let's make a new directory. We're going to call it secret. So this is just a brand new directory. There's nothing going on here, nothing weird going on, no trickery. Let's make some files in there. Let's make foo, bar, and baz. So we just have 3 new files in that directory. We can go ahead and ls it and we can see, hey, there's our 3 files. That's super awesome. That makes perfect sense. That's great. What are we gonna do now? Let's remove some permissions, okay? We're gonna take away the execute permission on it. So what does that mean? If we stat the file now, we can see if we look at its permissions right here, we have RW nothing RR. So this would be 644 effectively. This basically means this is like you would find most files are in this permission set, but this is a directory. So it's a little bit weird. What does that mean? Well, first things first, let's CD into it. We can't. Permission denied. But can we ls it? Kind of. How weird is that? So what's happening here? We are able to ls the file in the sense that we could list the directory entries of the secret directory. You don't need execute permission to do that. We don't need execute to list a directory, but we do need execute to go into it and do things like stat them. So in order to get information about the file, because ls does more than just list a directory, it gets information about each file in there. That's how ls can know if it's like a regular file or directory. That's why ls knows file size if you give it -l, things like that. You have to stat the file. So we can't stat these files, but we can list them. We could prove this if I were to fire up something like, let's fire up Python, let's import os.listdir. We can give it the name of the directory, which is secret, and you can see it can list it just fine, but we just can't go in there and do any work with those files. So what's next? Let's go ahead and re-give it that permission. So let's make things right, but let's take away a permission now. Let's take away the ability to read that directory. So we have execute back, but we can't read it. Might be a little confusing. I'll go ahead and stat it so you can see what it looks like. Here's what it looks like. We don't have the R permissions. We have these weird bizarro permissions. What is this? Like 311? I don't even know. This is just a weird permission set. So we can write to it as our user Dave, which we currently are. We can execute it, but we can't read from it. So what happens now? We CD into it. Hey, that works. That's awesome. What about if we ls it? Can't open it. Can't open it. I can be inside it. I have the read permission, but I can't, or sorry, I have the execute permission, but I can't list it. I don't have the read permission. So what does that mean? Can I make files? Yeah. Can I delete files? Yeah. I can't list files. I can't ls it, but if I know a file's there, like foo, I can delete it. If I try to delete it again, no such file directory, but I can't list it. So I have execute permissions. I can go in the directory. I can do things with the directory, but I can't read from it. I have write access, which allows me to change things in the directory. I should say that specifically. So yeah, super weird. Some really weird like Dropbox things you could make with this. I don't know. Typically, I just set my directories to 755 and call it a day. But yeah, hopefully you found this interesting. Yo, and of course, I want to give a quick shout out to my patrons over at Patreon. Thank you so much for your continued support. I think that's super awesome. If you want your name at the end of the videos like these lovely members have. Go ahead and check out my Patreon. You can see the link right there. Boop, there it is. Yep. So thank you very much. Appreciate the support. Yeah, have a good one.